The networking opportunities here at CppCon are well above and beyond any other C++ conference that I've ever been to.
So my name's Oleksandr, or in short, Alex, and I work at Snap on augmented reality specifically. And I think that's one of the most exciting applications of performance-critical C++. So feel free to talk to me about that. And in this talk, we'll be talking about mdspan and its potential overhead. But a lot of the findings are actually relevant to all kinds of complex abstraction you might want to build. So let's start by answering what is mdspan. Well, in short, it's a view over a multi-dimensional array, basically storing a pointer to its data and a layout. And it's designed primarily to use as a function parameter. But instead of trying to explain it in detail with more words, I think it's useful to try to get to an example as soon as possible and learn about that way. So what's the simplest multidimensional function that we can take for our example? Well, first, let's take the smallest dimension that's more than 1, which is 2. And the most common two-dimensional object is a matrix. Next, let's take some operations that's simple, but not too boring. Let's say matrix addition. OK? Now, to make sure everyone is on the same page, let's travel back in time into the high school times. When we were younger, the grass was greener, get some nostalgic feelings and all. Well, unfortunately, we're there just to remind ourselves about the matrix addition. So for our purposes, it's enough to think about a matrix as a two-dimensional grid of numbers. And when we add them together, we add elements at the corresponding positions. But if all those elements are continuous in memory, then we can just add them as ranges using std transform, which is available in STL, it feels like since the beginning. Yeah, so it doesn't really fit the topic of our talk. Let's try to make it more interesting. And while doing this, let's try to follow some standard. And for matrices, we have this BLAS standard, which stands for Basic Linear Algebra Subprograms. But unfortunately, it doesn't have matrix addition. I tried to understand why, and I'm not sure, but apparently because it was considered an operation that's too simple to be included. But I'm not sure. But anyway, to represent a matrix in here, we have a column which has matrix A and some LDA number. So let's clarify what that is. So that stands for stride, or like leading dimension. And while in BLAS, matrices are assumed to be column major, in C++, a more familiar order is row major, which is what we have in built-in CRAs. So let's take that for our example. And what the stride means that, OK, you have your matrix, but each row has not only values from that matrix, but also something else. Maybe we just took a block from a larger matrix. Maybe other values are uninitialized and are there just for alignment. For us, it doesn't matter right now. And if you follow the pattern in BLAS interfaces, we could write a function like this. So I tried to give all the parameters more readable names than in the BLAS standard. So we have rows and calls as sizes. And we have 3 matrices, each represented by a pointer and its stride. And the implementation is fairly straightforward. Well, Of course, it's not the most efficient one, but for the slides, it's good enough, I think. Now, looking at this simple code, how do you think how much assembly lines the compiler would generate for it? And to clarify, let's take clang at 02. So are there any guesses, like 10, 20, 100 lines? Well, just guess and we'll see. OK. Everyone's too afraid to guess. So in fact, it's 140 lines of code. And I'm thinking like, wow, compiler, what's going on in here? I gave you a couple simple lines of code, and I get this back. So I guess if someone claims that matrix addition is very simple, you could show this assembly to them. And when I see in code like this, I'm typically looking for longer lines. And in here, there are actually like 2 blocks looking suspicious. So let's zoom in into one of them. So in here, we actually see auto-vectorization in action. And this is the case when you have instructions such as move, add, and other common instructions, but with extra suffix like UPS, PS, PD, and etc. And like XMM registers or other like non-standard register names. OK, so vectorization is great for performance, but not great for slideware, definitely. So from now on, let's move to 01 land, and let's recompile the same code. So, OK, this looks like something reasonable to work with. Looks like it still has some vectorized piece, but it's small enough. So we'll take this as the baseline. And if you trust our compiler, this code should likely be slower, even though it has much less code in the end. Yeah, but let's quickly check it. I made like a basic benchmark using Google Benchmark. And apparently, it wasn't like too stable. So there are some outliers. But in general, the picture looks quite reasonable. So I took just square matrices with growing number of rows. And we see that for O2, we actually gain about 2x performance on larger sizes. But for small sizes, we actually have like worse performance. And this is also quite reasonable to expect, because there are too few elements to even apply vectorization on them. So there's a big piece of code that's not even executed in this case, and it takes some time to go past it. But if you care about performance for such low resolution matrices, then it's better to write like specific implementations with like compile time sizes. OK. So for now, we learned 2 important lessons. That first, like less assembly isn't always better, and vectorization also isn't always better, depending on the size of your data. Now that we have a baseline, let's try to write the mdspan version. And in here, looks like we're in luck, because there's a pending proposal called a free-function linear algebra interface based on the BLAS. And it's based on the mdspan. So let's look into the proposal. Well, in there, we have a definition that is quite general, and it's not clear how to apply it to our use case yet. But also, luckily, we have a reference implementation for the proposal. And in there, we have like this implementation. And I'll be honest, in my life, I was working with template code a lot. And I think this function has the most template parameters from what I've seen. And yeah, it also has like a wall of static asserts that I skipped. And the implementation in the end looks like it's optimized for column major matrices, not row major ones. But in general, it gives us a good direction to follow implementing our thing. But first, we need to answer two questions. First, like which element type to use, which is obviously float in our case. And next, which layout to use. So our BLAS-like interface specified one row stride, and elements in the row assumed to be continuous. So the column stride should be 1. And in the standard, we have layout stride, and it sounds like we should use it for that, right? Well, it turns out not really, because it has like this limitation that it supports only all strides known at runtime, not at compile time. So if we target 0 overhead, we definitely should aim to specify this like stride of 1 at compile time. So what are the alternatives? There's a pending proposal called padded mdspan layout. And I didn't read it too carefully, but from what I understood, it looks like it offers us to write something like this, use like layout right padded, and it should add like one leading dimension, like add a stride for one leading dimension. And in the comments, it says that a variant of layout stride was considered, but it was rejected because it's overly complex for the design. But actually, I think that it's indeed overly complex, but only given the existing mdspan design. And I think this line isn't too expressive. And I would really prefer to write something like this, where I can take just a standard layout stride and specify extents for it. And in there, I use an X notation for runtime value. So in here, we have two extents, both known at runtime. And for strides, I could specify clearly that only the first one is known at runtime, and the second one is always 1. And just reuse this layout in different mdspans. Yeah, so I need to make a disclaimer that in this talk, I'll be using a slightly altered mdspan design. And I just told you the first reason, but there will be more. But conceptually, like overall, it's the same and should have the same overhead. OK, so having all of this, I think we can finally formulate matrix addition using mdspan. So like we have two inputs, which I call LHS and RHS, and I believe are canonical names, and DST for output. And the implementation is quite straightforward. And note that in line 8, I'm not using square brackets operator because I don't have C++ 23 available yet for me. OK, so now let's compare the code that we have. And I'd like to have a quick poll. Like, who in here prefers the BLAS version using row pointers? OK, who prefers mdspan version? OK, so we have quite strong agreement here. But let's try to somehow measure this objectively, OK? If you look at C++ core guidelines, they actually have an item saying to avoid adjacent parameters that can be invoked by the same arguments in either order with different meaning. Now, looking at our mdspan version, if we have 3 spans where 2 are const and 1 non-const, like you literally cannot mess up calling this function because addition is commutative, so no matter in which order you pass the inputs, as long as the output is on its place, like the call is correct. And actually, if all of them are non-const, we could also fix this by somehow wrapping the output parameter and specifying it explicitly. Now, if you look at the left, then we can see, like, with pointers, the case is the same as on the right. We have just 3 pointers. But apart from that, we actually have 5 sizes, and all of them of the same type. So there are actually like 5 factorial ways to permute them, and only one of them is correct. And that is actually like 120 times. So we can objectively say that this code is 120 times worse, okay? But this is just from the design standpoint and API. But we're in here, hardcore C++ developers, we're primarily interested in performance, right? So let's look at that. And who thinks that we already reached 0 overhead using mdspan? Well, not much optimism yet. So let's look at the assembly. And yeah, it's still too big to compare in the same slide, but trust me, it has more instructions. And in this case, it's not like factorization where we have like useful instructions added. It's just the same code, but with some extra instructions in the middle. So I thought about it and looked at the functions that we have, and there's like a straightforward fix we can make. Actually, in the BLAS version, we're passing matrix sizes only once for all the matrices. But in the mdspan version, each of 3 parameters includes those sizes, and they must be equal. Yeah, so that's a clear overhead, and let's try to fix this. And I'm not sure if there's a way to fix it with the standard design, but I had an idea which I think is quite interesting, so hear me out, okay? Actually, if you look at the layout stride, or like any layout, its primary responsibility is to map a multidimensional index, which is just a sequence of int indexes, into a single offset for the pointer. And for layout stride, I took a formula from the standard. This mapping is a dot product of strides times this multi-index. So it actually depends only on strides and not extents. And extents can be used for bounds checking or to identify the size, but we don't need it in our case. So we could relax this layout concept to require only mapping. And in that case, it's valid to have what I call layout strides only. And after this, we might say that it's not valid to call our thing mdspan after this. Maybe it's like an md pointer or something. But I guess it's not too important, so let's continue to use mdspan. And having this, we can actually fix our issue. We can use this layout with only strides for 2 of the three arguments, and extents are passed only once. So do you think this solved our problem and now we have 0 overhead? Yeah, not much optimism again. And indeed, this really helped us. We got from 42 down to 35 lines, but the original target was 32, our baseline. And actually, before going forward, let's check even if it's worth looking into. So again, I made a simple benchmark with the same sizes. And actually, for larger sizes, I would expect numbers to be roughly the same, because just having an extra instruction shouldn't be too bad comparing to actual arithmetic performed in this case. But yeah, the results are quite unstable, but on average, it feels like they're almost the same. Maybe mdspan has a bit of overhead. I just took one run, so there are outliers. But for smaller sizes, there's definitely consistent overhead, because we do more instructions and very few computations. Okay, so because we had like, assembly too big to fit on a slide, let's try to find an example which is as simple as possible, but hopefully it should reproduce our problem, and hopefully we can fit assembly comparison on a slide. So for that, I took just filling a matrix with a value, and matrix is like, the same concept with the stride, and code is very similar to what we had for addition. And indeed, if you look at the assembly and align it so that similar lines go together, then we clearly see that mdspan version has an extra block of instructions. And for the reference, RSP is the register for the stack pointer. And it looks like we're loading some memory from there. And this is very weird, why we have the stack access in one case, but not in the other, because the computations are identical and we're passing like, the same data, basically. Like, and actually, this was the place where I got stuck for a few trying to understand this. So a few years ago, Chandra had a great talk at this conference, doing a similar investigation to ours, but for a unique pointer. And he was also looking at the assembly, and you can see he also has RSP in the slides, so this looks promising. And actually, after the talk, in the QA section, there was a comment about trivial ABI. Yeah, so let's check if that comment helps us. Well, I've got bad news and good news for you. Let's start with the bad ones. Well, it doesn't really help. Indeed, I thought maybe I made some mistake in the implementation, but I checked all the traits, like for trivial copy, move, destruction. Like the actual trait is trivial doesn't apply for mdspan, I believe, because I actually initialized the pointer to 0 in a default constructor. But it's not the thing that matters in here. And I also verified that the size is indeed the same as the size of one pointer and the 3 sizes that we passed. Yeah, but this also we have good news, that we'll likely learn something new today, okay? And then, like a blessing in disguise, I found this Stack Overflow answer, which is actually quite long and very comprehensive, so I took only a relevant part from there. So the second part talks about POD, and in the example has this custom copy constructor. And this was exactly our first suspect, but we already checked that. But the first item says that if the object size is larger than 82 bytes, it is passed in memory. Yeah, and immediately it's clear that it's a problem for our mdspan because it's larger. And I'm curious, so in here we have like very professional C++ developers. I'm curious how many of you knew about this limitation before. So like, yeah, a couple of people. But yeah, this was definitely new to me, so thank you very much, Margaret. And I'd really appreciate if you went to Stack Overflow and uploaded this answer. It's really a good one. OK, so armed with this knowledge, we can implement a solution. And unfortunately, we cannot use our original mdspan because it's just too big. So we somehow need to split it. And actually, one fairly clean way to do that I found is to separate extents, which are exactly like 16 bytes. And for the mdspan itself, again, we're using our stride-only layout. And after that, the code actually looks almost the same like before. we still continue to use mdspan. And who thinks that after this we reached 0 overhead? I mean, in performance. Still too pessimistic. But yeah, after this, we actually have identical assembly with just a few registers named differently, but the instructions are completely the same. So this looks like a success, right? But let's get back to our addition example. And indeed, we can apply the same approach and also avoid extra stack access. But after doing this, I noticed something interesting. If you look even at the original implementation with just row pointers and sizes, it still has some stack access. And why is that? We're not even using any abstraction. Well, turns out there's a System5 ABI, which tells us that parameters to functions are passed in the registers listed, and further values are passed on the stack in reverse order. So this means there is just 6 registers for parameters. And if you look at our function that we started with, it actually has 8 register size parameters, which are either float or size t. So I'm not sure how to completely solve this issue. If we know that our extents are small enough, say we don't have matrices with more than a couple of billions lines, we could use a smaller type for that, say uint32t. And this way, we can actually save like 1 stack access, if you care about it. But OK, we have this low-level function. Let's get back to the user API. So of course, improving performance is good. But if for that we are making our user to somehow manually split their multidimensional arrays into pieces, that's not really good. And that's similar to the BLAS API we started with. And to be honest here, I don't know what's the best solution. So maybe you have a better one. But I have at least one idea. I think what we can do is to write a wrapper on top of that, which would take any kind of multidimensional arrays. And it would be good to have a concept for that. It could check that their element types match, and their compile time extents match. We also could make it always in line, because it doesn't do much work by itself. And we might want to avoid the extra overhead of calling a function. So what can it do? It can assert that all the extents are matching, and do this only in debug builds. Also, we might check that if destination is a resizable container, like resizable MD array, we can first resize it to the output size. Otherwise, we just check that its size matches, or its extents. And after that, we call our optimized implementation, like taking all the data from the inputs. And I think on top of that, it would be really nice to write codes similar to the one we write for like primitive types, just like as an arithmetic expression. So for that, unfortunately, it's not that easy to implement it, because we need to, from the right side, first we need to create an expression template. And on the assignment operator, we can call our add function from the previous slide. But in this case, we can actually make some more optimizations. If one of the inputs is passed as our value, we could reuse its storage if it's a container, and just write output in there, potentially. OK, so it sounds like we're good. We have abstractions that actually produce 0 overhead at runtime. we have an idea of how to nicely wrap them for the user. So looks like we can celebrate, right? Well, actually, we forgot about the ultimate test for any C++ code, which is called window. To make mdspan compile, I had to fix several internal compiler errors, which just tell you, OK, try to somehow modify your code around this line and hope that it will work. OK, but even after dealing with this, well, of course, Microsoft has a different calling convention. And their x64 ABI uses a 4-register fast calling convention by default. So it's 4 instead of 6 registers. But it's not the main issue. Additionally, any argument that doesn't fit in 8 bytes must be passed by reference. And actually, this has consequences even for stud_span, the regular one, because it has 16 bytes, not 8. So just replacing your pointer and size parameters with span will change your assembly on Windows. Do we have a question? Oh, OK. And in general, it looks like to me that Microsoft just doesn't like high-level abstractions. Yeah, but let's check this. I generated assembly for our fill functions. And indeed, for mdspan, we can see that there are much more instructions. And a lot of them are accessing memory, which you can see as in the lines where keyword PTR is mentioned. Unfortunately, I don't have a Windows machine to benchmark this on, but I'd expect mdspan version to be slower. OK, so we get to the conclusions, which, to be honest, are somewhat upsetting to me. Because doing the best thing is much more difficult than it should be. And regarding efficiency of your code, there are a few things to remember. First, for efficient passing of parameters, they should be passed in registers. And for that, you need to make sure that they are trivial to copy and they're small enough, which is just 8 bytes on Windows, which doesn't leave much space to work with. So this means that at the low level, we might have to stick with actual rolled pointers and ints. Maybe in the implementation, we could create mdspan from it to simplify the code, but that would likely add some overhead. Also, we shouldn't pass unnecessary parameters to the functions where performance is critical if we use those parameters just for assertions inside the function. Because we have only 4 registers on Windows for that and 6 on other platforms. Also, but the nice thing that we can actually hide all of this complexity from the end user behind convenient wrappers, which could potentially be inlined. And the conclusion for mdspan that unfortunately it seems not flexible enough, at least for these cases aiming 0 overhead. And it may be too late to fix it in the standard, but we'll see. So this is the end of the main part of my talk. So thank you for the attention, and please ask questions.
Hi. Thank you for your talk. So a lot of the authors of the papers you talked about in your talk are in the audience.
That's good to hear.
Have you attempted to contact them?
Yes, I did.
You did? That's excellent. That's good. Did you report the ICEs, the MSVC bugs, to the implementers?
That one's not yet. Oh, Yeah, I think I reported some of them, but some aren't easy to like reproducing a minimal example.
That's good. Okay, so I want to elaborate a little bit. Sorry, I'm kind of monopolizing the mic, but I want to talk a little bit about the difference between mdspan as a function parameter and multidimensional iteration.
Okay.
Okay, so I might posit that the multidimensional iteration algorithm that you present there is perhaps not the fastest. It's a generic algorithm that's effective for generic layouts. But if you have information about your layout, you might make different choices. And that could affect performance of the function. And while I've spent some time reading the early BLAS papers and the drafts from the 1970s, and probably the reason they didn't posit a matrix add is because they were interested in focusing on performance primitives that they would have to implement using assembly instructions. And the logical performance primitive is a contiguous add, a vector add. And a matrix add would be a loop over vector add. So that's probably why the BLAS didn't include it.
Mm-hmm. Okay, thank you for the info.
Yeah, but I just wanted to see if you wanted to elaborate perhaps on, and also if you had perhaps read the mdspan paper from, say, 2019, which gives a lot of performance results for different kinds of iteration?
Well, in this talk, I took like a specific example, not a generic one, but specific like strided example with known layout.
Sure.
And the goal was like not to implement some like best generic iteration, but to compare the overhead which mdspan gives as a function parameter.
Okay. Let's talk more offline.
Yeah, let's talk later, but just to clarify that this wasn't the goal.
Right, but there were papers on performance from before, and it would be interesting if you had compared performance results with those, but sure, thanks.
Yeah, probably I could. Yeah, thank you.
Hi, thank you for the talk. I just wanted to clarify, maybe you can elaborate a bit more about, so I think in the later part of the talk, there were a lot of optimizations based on like how we pass function parameters. But I was wondering why wouldn't the compiler be able to just like at the start of the function, load that from the memory, and then when you do the iteration, it would just be like normal, like the same thing. So it would be just like one load at the start of the function, one like load of however size your mdspan is. Like I think there was one example where the extra code was actually in some loop, but I was wondering like why couldn't the compiler like see that? Is it because like the compiler couldn't reason or something, or is it the compiler just not smart enough? Like, is there actually some reason why we're doing extra loads in the middle of the loop?
Yeah, so actually those two lines, they are exactly like loading from the memory into the registers. I think it happens before the loop.
Oh, okay.
And the reason like why they're necessary because of the ABI limitations that I described.
I see. So it's only once per function, right?
Yes.
I see.
Go back to the earlier slide where you had this.
Like this comparison.
Where you had the BLAS and the mdspan next to each other.
Do you mean the code?
That one.
Oh, that one. Yeah.
Right. The extra loads are in the function prologue. Are they?
I see, yeah. I think it's only like once per function.
Yeah.
That's the function prologue.
Yeah.
And before them, there's no label for the jump. So yeah, this code is executed just once.
But then you profiled it, right? And you noticed like a visible slowdown, right?
Well, for small sizes, it was visible because for them, there are like few computations.
Ah, I see. Yeah. Yeah, thank you. That makes sense.
Okay, so if you don't have more questions, I have some bonus slides. Yeah, so far we've been talking about matrices, which are just two-dimensional and probably not a very exciting example for mdspan because, well, we had matrix libraries available for decades in C++. So let's try to take some practical example of higher dimension. And I think for that, a good example is an image. And I won't try to fully answer a question, what's an image, in this talk. For that, I'd refer you to this talk from previous CppCon. And even that talk doesn't answer this question fully in an hour, so I won't even attempt. But for our case, we can focus on the image representation for like the simplest images. And I believe there are two approaches. One to view them as a two-dimensional array of pixels, and the second one to view them as a three-dimensional array of scalars, but where the last dimension is treated as a pixel, and which has a specified color space. And I think the first approach is conceptually simpler, but the second one also has its benefits. In particular, a lot of image operations don't actually care about the color space. They only care about all the sizes and scalar type. And those are all the like slicing operations, copying those slices, and also alpha blending, and so on. So those are inherently just multi-dimensional array operations. And for them, we can avoid generating identical assembly for different color spaces without relying on non-standard identical code folding. And also, like one interesting case is that it allows us to formulate in-place conversion of color spaces, say from BGR to RGB, which wouldn't make sense if you had like a strongly typed RGB pixel in the image. And also, it's just a good example for this talk, for higher dimensions. So from here, it's not actually working code, but a draft to visualize the idea. But what we could do for image layout, similarly to compile time extents and write time extents, we could have a color space template parameter, which is either known at compile or runtime. And because of that, we store it as a no unique address to avoid extra size if it's known at compile time. And as before, we store rows and columns. Similarly to BLAS APIs, we store a stride, and it's actually needed for some of the images we get from native camera on some platforms. So for such image, extents are defined as rows, columns, and the last dimension is just the channel count from our color space. And strides have this custom stride as the first parameter. And yeah, it seems like a standard or like pending to the standard layout right padded could represent this use case, at least the strides. But I believe standard mdspan requires extents to be a one of the specializations of the standard type, which just stores all the values. But in here, the last dimension is defined by a color space. So I'm not sure if it fits. Yes?
With extent as it is in C++23, you could say that it's compile time and stuff.
No, I mean, it's either compile time or runtime value, but it's computed from the color space. It's not stored directly. So we don't store this value. So I'm not sure if this can be represented. And then let's look at like the most common image operation, which I think is an RGB to grayscale conversion. I think everyone conceptually knows what this is, so let's continue. So to implement that example, we could somehow define color spaces. And in here, I define them as like a tag dispatch structures conceptually, and somehow specify their sizes at compile time. It's not important, the exact mechanism, but you need to know that they have 3 and 1 channels. And after that, the conversion code could look something like this. We can have two images with like color spaces specified for the image layout. And we have a similar loop to what we had before. Like in line 7, I'm using a subscript operator, which we don't yet have in the standard, but it could be implemented using sub-mdspan. But I'd really like to have such operator in the standard, which specifies only the first dimensions and then gives you a view over the remaining ones. In this case, the pixel. It's like the way it's working in NumPy and also in many C++ libraries. And after that, we can do a conversion using commonly used factors for RGB channels, which are derived from like human perception color, human color perception. It's like not the only approach to this, but one of the most common ones. And this code looks fairly good using mdspans and quite expressive, I think. So yeah, now that's all I have. Thank you again. Okay, any more questions?
Can you do just an MD span of pixel objects?
Yeah, as I said, it's like one of the options.
Okay, I missed that part. I'm sorry.
Yeah.
I got here late.
It was like a few slides before.
I'm sorry.
Yeah. Okay then, thank you everyone.